Hello everyone, I am Xiao Gang. Okay, last class we briefly talked about removal. Okay, this class will talk about sorting. Yes, sorting. Look at the structure here. It sorts using a method that passes toy-dimensional coordinates. But note that when doing this kind of sorting, that is, when you modify this container, this sort order will become invalid. So please pay attention to this point. Then let's take a look at. For the first type of sorting, this calls fstream. It defaults you overloading the size property. It says that it sorts by putting the largest ones first. It compares them by their alphabetical order. Right? Then this, and then the two of them are equal. So they are compared in the second place. So E is greater than A, so he is positioned a little bit more forward than him. So looks like this. When comparing this, it's just a comparison of length. Right, as for this length, this is how this type of data is sorted. If the lengths are the same, it might be that, it may not always be. This shouldn't be a stable sort like this. Let's just implement this for now. If you want to apply it to a struct, it's the same way. We just need to implement the related functionality. This requires us to have a fruit. In order to achieve the desired result, we might need to initialize this fruit the same way. Let's see if we can initialize it this way. Let's have it perform a privacy conversion. Just place it like this. Okay, this looks like its privacy conversion is normal. Then, in order to ensure that our sequence is different, we can just move it to this position. We move this to the middle. Then we execute this. Then I will directly enter the breakpoint here. In order to avoid its issue, I can write another one. Okay, I will directly enter the breakpoint. Okay, the points on our side have come in, and this is the TSet we initialized. Our data is like this. And after we let it go through a sort, we find that this order remains consistent with this, and then we let it go through another one, this kind of sort based on our binary positions. You will notice that the order is... Actually, let's take a look at the length of this uniform, because it is unstable, as you can see. So these two are the same. So you can't be very sure about them. They are in the front. We can point out this area at the back. This is a sort. It provides a sort for this class. Actually, we should. Let's try this. Click in here. You will notice there is also a stable sort here. This is for stable sorting. There are also some other methods. Look at sort or remove and so on. Okay, we can paste this method in. This means it is a stable sort. Right? We must pass a binary position like this. Okay, then let's continue looking down. This is a simple sort. Then let's look at this operator. It's just this equal sign. It can assign this value to this value because it is a regular value type. Actually, these are two sets. They are both values relative to each other. These elements are mutually unrelated. So it's a kind of generated term. Then we can implement it. We call it operate over TSet. And we still need to pay attention to smart pointers and these types of pointers for our UObject type. They are all pointers, but they point to the same object. And if you operate through a pointer, even though it copies another pointer, if they operate, they are pointing to the same object. So that's what it means. We need to pay attention to the difference in this area. So we can pull this number over here. So it can perform some parameter additions and changes in this new state. And it won't affect our old original state. Then I'll just connect the segment point here. Okay, the segment point has come in here. And here you can see there are 6 elements. We copy the set. We perform a simple add, delete, modify, and query. on the second element. We added a sample, then we removed appear here. Then finally, actually this original one, it doesn't have the sample, but its peer is still here too. So this is the operator this way. We can make a copy of the generated one. Then let's continue to look at our Slack. It is not the same as TMap. This way of understanding Slack, we can see that Slack does not include the memory allocated for elements. We can use reserve to ensure that it can store at least one element. And thus, there is no need to additionally allocate memory. So, to release memory, we can use reset or empty. Slack is this element called Slack. It optimizes the process of adding new elements because it can use pre-allocated memory instead of allocating new memory. It is also very efficient because the system is not deallocating the memory. It just releases the object. So, if we are clearing it and just want to release the objects or fill a new collection with the same or fewer elements, this method is especially useful. You can see that this Slack, it won't actually free the memory inside. It only clears out the elements inside. So these are all some Slack elements, and then we can directly use reverse to create these kinds of Slack elements to pass to pre-allocated memory before adding elements. So this spot guarantees that it can store 10, and then this spot, and then we sequentially add these 10 kinds of fruits into these 10 spots. And then pre-allocating Slack causes the addition of new elements in reverse order. So regardless of the order, actually, we don't care about this order because you shouldn't worry about the order either, because sometimes paying too much attention to it, the order might actually cause you to make coding mistakes. You can just assume that it is unordered. And then this area handles the removal. It's equivalent to removing this, so it should be for these elements. So it just removes the skipped positions, right? And then it strikes it, and then you will see that only this last one is struck. So what should we do at this point? Actually, we do it through compand or the CompactStable function. Combine them into strict. And CompactStable can maintain the strict sorting, but we suggest that you just ignore the order. At this point, uniformly inherit it as unordered, and then you don't have to worry about the order. Okay, so let's add a method here. Okay, we call it selectSet. Okay, if we look here, let's take a look. First, here, reset just releases. We don't need to demo the reset anymore. This will generate some. Let's demonstrate that instead. So, the client requested a reset here. Then we reset it. Then these elements should be cleared and set to this type of element. At the same time, we can perform a capacity increase. Because originally, we definitely didn't have 10, we let it expand its capacity to 10. Then we have it execute a loop to add our elements into it once. Then, after we finish executing, we are going to remove it now. After removing it, we will only see this. We can see this empty space. Then we can just crop it one more time. This spot is basically where we stabilize the cropping. Then we'll drag it over here. Then we can click here to look at this detail. As you can see, this pre-allocates enough memory to contain elements. We've talked about this reset before. As much as possible, it will save as much of the allocated capacity as possible. It's the memory or capacity or something like that. Okay, this removes it right here. And then at this place, circ. So this place crops the element, right? Thereby avoiding the slick of yes, and this CompactStable is to compress the set. And it won't change the sorting inside it. Yes, and it won't leave gaps or empty spaces like that, but this might change the sorting. Okay, in this case, circ trimming. Now, I will directly show you this section. Let's see if this result meets our expectations. Okay, the point here has already come in. After we enter, we open this local variable. We have a number here, right? We haven't defined it in this place yet. Let's define it first, okay? Now it has 6 elements. Its max is also 6. You see the elements, right? We can look further down. There's this one. Then after we reset it, Let's look inside the element. This data, as you can see, is gone. It's just empty. It has already been cleared. Then let's reverse this. You'll notice that this spot generates 10 invites. Meanwhile, its maximum is 29. Look at this element. Okay. Next, if we look at this, we keep adding this element here. As you can see, after adding each one, the elements inside this element are added in. We can take a look like this. You will find that it was added here as 0, 1, and 2. We don't care about this order. You also shouldn't worry about this order. Doing it this way will actually create some problems for yourself. Okay, here according to 0, 1, and 2, it has 7, 8, and 9, and then it will remove 0 here, right? After removing it, it is gone, but actually click this row value here. Find an element. This place is a slack element. This one is invited. Then let's remove it. Okay, we skipped it. Actually, you will find that this last element, you can see some empty spaces in the middle, but this last one is no longer an empty space, right? This last one should be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, the last one was originally an empty space. So this Sirac cannot delete these elements in the middle. But what you should notice is his max here. His max has become 10. We can drag this code back a bit. Drag it here, dragging like this. Or we can drag it to the very top. Let's execute it again. Look, this spot is 29. We make it execute all the way to this spot. To prove this Sirac, he deleted everything after this. This spot is basically just keeping a 10. Right? So we leave them here. We delete all the space after them. Then, for the countable, we'll make it compressed. You can see that this area was compressed. Here, it removes all the empty space in the middle. Then let's have it share something here. It executes successfully. This workflow is actually quite similar to the previous ones. Interesting. You can click in here to see how these parameters allocate the internal layers, how to handle these base values. Alright, so let's wrap up our discussion on Slack here. Thank you everyone.